All right, so there's another way to algebraically interpret vectors, okay? So remember that a vector is something that has both direction and it has a magnitude or a length, okay? Well, there's another way to give those two quantities. So here I have a vector, and I've told us that the length of this vector is 2. So we're going to call this vector u, okay? And what do we know about vector u? Well, right now, we know that the length of u is 2. So we've given that information right there. The length of the vector is 2, okay? Now, the other thing that we need to define a vector is we need a direction. Well, one way to get the direction of a vector is with an angle, okay? So we can think of the position of the vector or the direction of the vector as given by an angle with our x-axis. So in this case, our angle theta that's defining our vector is 60 degrees, okay? With those two pieces of information, we have uniquely defined a vector. So this vector has magnitude 2, and it makes a 60-degree angle with the x-axis, okay? That angle is called the direction angle for vector u. So this is known as the direction angle, okay? This is the magnitude. The direction angle is always a positive angle with the x-axis, okay? Now, sometimes what we want to do is we want to translate from vector information given like this, so given with a magnitude and a direction angle, into our horizontal and vertical components. So remember, that looks like this: horizontal component, vertical component. Okay, well, how can we do that? How can we go to something that looks like this to something that looks like this? Well, the answer should look familiar to you because this is exactly what we've been doing with our right triangle trig for pretty much ever. Okay, what do I mean by that? Well, let's look at this, right? Our horizontal component is going to be right here, right? This is our horizontal component. And how do we find that? I don't know why I put a period there. Well, think about a triangle, right? Our vertical component is going to be right here. This is going to be our vertical component. But this makes a right triangle. And haven't we been doing stuff with right triangles pretty much all semester, right? How can I find this piece right here? Maybe we'll call it, I don't know, x, since it looks like an x value. How can I relate 60 degrees to an x? Well, this is adjacent. So wouldn't this say that cosine of 60 equals x over 2? Or in other words, x equals 2 times cosine of 60 degrees? Seems to make sense. Do we know what cosine of 60 degrees is? I think we do. Cosine of 60 degrees, if we pull out our unit circle, is 1/2. So this says that x equals 2 times 1/2, or x equals 1. So the horizontal component is 1. Okay. How about our vertical component? How can we come up with the vertical component of this vector? Well, the vertical component, which we show in blue here, okay, the vertical component, which we'll call y, the vertical component is going to need to relate 60 degrees, y, and 2, the length of that vector there. But isn't that, can't I say something like sine of 60 degrees equals y over 2? Sine is y over r, okay? So that tells me that y is equal to 2 sine of 60. But what's sine of 60? Sine of 60 is square root of 3 over 2. 2's cancel, which tells me that y is the square root of 3. So my vertical component of this vector is the square root of 3. Okay. So here we have taken a vector that's given to us with a magnitude and a direction angle, and we've translated it into its horizontal and vertical components. Okay. Let's do another example that looks like that, and then we're going to go the other direction. All right, so here again is a vector defined by its magnitude. So we're going to call this vector v. So what do we know about v? We know that the magnitude or the length of V is equal to 4. And we also know the direction angle for V. Remember, the direction angle is always given from the x-axis, and it's a positive angle. So our direction angle is 315 degrees. Okay. Now what we want to do is we want to translate that into, so we want to go from magnitude and direction angle into horizontal and vertical components. Okay. So how do we do that? Well, in order to do that, we need to think about this in terms of a triangle. Okay. So let's think about this for a minute. Now, eventually we want to get kind of a shortcut for doing this so we don't constantly have to sketch this out, right? So how can we do that? Well, if we're thinking about this piece here, right, how would we normally do that? If we knew an angle theta and we knew our 4 here. Well, what we would do is we would sketch in a reference triangle. Think back to kind of very beginning of this class. We'd sketch in a reference triangle. Okay, so there's our reference triangle. And we'd use that reference triangle and that reference angle to figure out our y value and to figure out our x value. Okay. And that's exactly what we can do here. So first, let's think about our reference angle. Right? Our reference angle is going to be right inside here. And to find our reference angle, we're going to take 360 and subtract 315. 360 minus 315 gives us a reference angle, theta prime, of 45 degrees. Okay? And now we're going to use our sine and cosine relationships to find our x and y. Our x is going to be given by cosine of 45, looking at this triangle, equals adjacent x over 4, okay, which means x equals 4 times cosine of 45. And then we're going to have to think about sines here, just like we've always had to think about sines. Our x should be positive, right? Okay, so we can do x equals 4 times cosine of 45. What's cosine of 45? It's the square root of 2 over 2. Okay. 4 over 2 cancels, leaving with just 2 square root of 2. So the horizontal component of this vector is 2 square root of 2. Now to find the vertical component, right, our y, well, using kind of our old school reference triangle, we know that sine of our theta prime, or sine of 45, equals opposite y over our hypotenuse, which is the length of the vector, 4. So we know that y equals 4 times sine of 45. Now here we need to think, notice that y is negative. Y is going down. Okay, so we know that this y should be negative. So when we get our final answer, we'll have 4 again times square root of 2 over 2. Since sine of 45 is square root of 2 over 2, we have 2 square root of 2, and it has to be negative. Okay, so that's negative 2 square root of 2. Okay, so here is a little bit of a handy shortcut for doing this. When we have a magnitude and we have our angle, okay, a direction angle, well, we can sketch out our reference triangle to find our horizontal and vertical components. That will always work. The other thing we can do is think in general about these relationships, right? Our y is always going to be related to the sine of an angle and our magnitude, the length of our vector, right? In other words, our y, okay, our y component, which is our vertical component, so y, which is our vertical component, is always going to be equal to the length of our vector, okay, times the sine of our reference angle, okay? So what does that mean? Well, it means we can kind of short circuit this. If I use my handy dandy calculator, okay, I'm going to real quick make sure that my mode is in degrees, which it is. And I'm going to look and see what happens when I multiply the magnitude, which is 4 times sine of our original angle, 315. Now our calculator knows that that should be a negative, so it gives me negative 2.828. So it gives me negative 2.88. Okay, or negative 2.8, which, if I, over here, look at 2 times the square root of 2, Well, that's also negative 2.82, right? So this gives me a nice way of finding at least decimal approximations. If we want exact answers, we're still gonna have to work this out the long way, or we can just look at our reference triangle, right? Not our reference triangle, excuse me, our unit circle, right? From our unit circle, if I think about, right, our sign we said was that 315, my unit circle will tell me that I can do 4. What's sine of 315? My unit circle tells me it's square root of 2 times 2, a negative square root of 2 times 2, which gives me that negative 2 root 2. Okay. Now if I want to do the horizontal component, our x, which is the horizontal component, well, again, the short circuit here is going to say that x is equal to our magnitude times the cosine of our reference angle, not our reference angle, our original angle, our direction angle for the vector, which says that x, in this case, is going to be equal to 4 times cosine of 315. Well, using our calculator, we can get a decimal approximation, or using our reference triangle, right? I know that 4, or, sorry, cosine, excuse me, of 315 is the square root of 2 over 2. So I again get to 2 times the square root of 2. Okay, so this shortcut method will work anytime that we're given a magnitude and a direction angle, and we want to change that into a horizontal and vertical component. Okay? Now, what if we want to go backwards? What if we're given a horizontal and vertical component, and we want to come up with the magnitude and the direction angle? Well, we can do that too. So that's what we're going to do next. Okay, so remember that if we have something with a magnitude and a direction vector, to go to component form, we can take the magnitude times the cosine of the direction angle, and then the magnitude of the sine of the direction angle, and that will give us our horizontal component and our vertical component. Now, what if we want to go the other way? So what if we have a vector, something like 2, 3, okay, and we want to go from this horizontal and vertical component to a magnitude and a direction angle? Well, let's sketch this vector real quick. So 1, 2, 1, 2, 3. So I'm going horizontally 2 and up 3. So here is this vector. So how do we go from these two things to these two things? Well, remember, the magnitude is fairly straightforward. To get the magnitude, I'm going to call this vector u. To get this magnitude, we do the square root of the horizontal component squared plus the vertical component squared. Okay, that gives us our magnitude. What about our direction angle? Well, our direction angle is right here, okay? And our direction angle, right, realize if I think of this as my vertical part, that's 3 for this particular vector, and this is 2. Well, how is theta, the opposite side, 3, and the adjacent side, 2, related? Well, tangent of theta is equal to opposite over adjacent, or 3 over 2, okay? So to go from here to here, we can find the magnitude using square root of the horizontal component plus square root of the vertical component. And to go from, and to get our direction angle, we can use a tangent relationship. Tangent of the direction angle is going to be equal to our vertical component over our horizontal component.